2. Okay, so last lecture we made a start with the sequential circuit, and we learned the basic latch function. So we went through the SR latch with active low and active high enabled. So we learned the basic functions, or the very popular, one of the very popular application of latch. So that is to design the D-bounce circuit. So the VHDL code for latch is the simplest VHDL code you can get. So that's just to for the output to follow the input. So I'm going to have a quick review of this D-latch VHDL code because we are going to use it right after this for the primitive component instantiation for this D-latch. So the function of the D-latch is the output is going to follow the input when this latch is enabled. So it has one input, one output, and one enable signal. So in this VHDL code, all of these input outputs are defined as a BIT data type. So for this BIT data type, bit data type, we only have 0 and 1, two different values. If you define it as a standard logic, then it will, each bit will have can have 9 different values. Okay, so for this D-latch, we also learned that is a transparent latch. So output follows the input when enable is set to 1. I mentioned that this if then statement implies there is an else statement there. It is not explicitly written here, but if you would like, you can complete this statement with an else statement. In the else statement, the Q will get assigned with Q. So it will keep its previous value. So that is what these if then statements imply. Okay, so process we learned. Whenever you see a process or whenever you want to program a sequential circuit, you have to use a process. And within this bracket, we are going to list all the input signals. So this is what we call a sensitivity list. If you don't list these signals here, that means the process will not run. So the process will only run when any of the signals that we list in the sensitivity list changes value. So that is when the process is going to run. Okay, so the next step is to instantiate a latch primitive. So now we know what the latch VHDL file looks like. So that is what we just saw. So the next step is to instantiate it as a component. Although here we are talking about the cortex or Altera components. With Xilinx Vivaldo 2 is going to be, I would say, very similar to what we are doing here. You have to include these 2 lines also in Xilinx Vivaldo 2. And what you don't need to do is the library, because in Xilinx 2, when we are using Xilinx Vivaldo software, it already knows that you are going to use its library. So you don't have to really includes the additional Xilinx library there. It will be treated as by default is already included. With Altaria, you will need to add these 2 lines of library code. So for the entity, latch primitive is port. Pay attention that we are defining these 3 ports with this name d_in, enable q_out. These are the external ports to this new entity that we are defining. The entity name is latch_primitive. And all of them are defined as data type SDT _ logic, standard logic. Okay, so within this entity, we have the architecture A of latch _primitive begin. So here we got components actually. So this is the components is already included in the library we added at the beginning of this HDL file. So the latch _ primitive latch. So that name we have, following that name we have port map. So this part, within this port map, we have a bracket. So within that bracket, we have D get assigned with d_in. Remember this d_in is what we defined as the input port to this entity. So that is the input port of this entity. Which entity? We defined latch _primitive. This is the entity we have with this within this HDL file. But this latch, so this latch component we have here is already defined in another HDL file that is included in the library. All you can see is in another HDL file. So the port map here, so the first D here is the input port of that component entity. And we are connecting it to the external input port of d_in, which is defined within this HDL file. So for adding port map in the future, when we are using adding components, you would know that the first name, the first port name here is so corresponding to the port name of that component. And it gets assigned with another port name. And the second port name that it's connected to is a port name we defined for these new HDL files, external port. Or in another case, this can be an internal signal. So we have to be clear here. Another example here, ENA. So this ENA is the internal port name of that component, and the enable signal is the external port we defined previously for this HDL file. So the last one, Q, is the internal port name for this component, and Q_out is the external port of this HDL entity. Okay, so we will see a few more examples in the future. So this is just a quick recap. So multi-bit latches in HDL. This is actually simple. We will use another generate statements to instantiate 4 parallel components to indicate that we are having 4 different bits. You can easily extend that to multi-bit like 8, 16, 32. So in this behavioral description, we are using standard logic vector, and they are controlled by a single enable bit. So for this latch component, we still use these two lines to indicate is the IEEE library and the standard logic 1164. So this standard logic 1164.all, it is required for standard logic types. So we are using the standard logic and standard logic vector. So both types are included in this library. And this library LPM is a library that is provided by Altair Cortex for the LPM component. Okay, so latch 4, that means we have a 4-bit latch. The port we have D_in. So now this port is defined as standard logic vector, bit 3 down to 0, so 4-bit. Enable input port is still a single bit standard logic, so 1 single bit. The output of this latch is Q_out, that is another 4-bit standard logic vector. So this is the port definition. So within the main architecture, we have latch 4 and generic map. So I'm going to explain now what this means. So within that library, this VHDL code includes a generic definition. So the generic definition is a parameter definition. It defines the number of bits to be included or to be generated. So the LMP_width is the number of bits that's we're going to define for this latch. So here we are giving it 4. That means we are defining it with as a 4-bit latch. So when we write VHDL code in the future, we need to learn how to write a generic code. So let's say we are going to write down the VHDL code for the latch component. So in the at the beginning of that VHDL code, you will define a generic parameters that is the width of the number of bits you're going to use. So simply this is going to be redefined in the future. Whenever you are going to use this component, you need to give it a number of the number of bits you want to define. So this piece of code can be used flexibly. So that is how we define the generic parameters for code. This will appear in many different IPs, but normally you will get a default definition. So if you don't define it, this will be a default numbers. So it depends on what the default value is. Without changing it, it will be defined as a default number. So here we are redefining this width of the generic code as 4. That means it's a 4-bit latch. So for the port map, it's going to be the same as before. So data, so for the data here is the internal port name of this latch 4, and D_in is the external port of this VHDL file that we are writing. Gate is again the internal part of this LPM underscore latch. Enable is the external part of this latch for underscore LPM HDL file. Q is the internal output port, and Q out is the external output port of this HDL file. So a simple rules here is always remember the first name here is always going to be the internal part name and followed by the external part name that we want to connect this internal part to. So this is how we define the port map for the component. Okay, so the schematic layout of the latch, it will look like this. If you generate a similar schematic in Vivado 2 using the within the Xilinx Vivado, you will see the similar schematic component. Okay, so that is the latch. So the next important concept we are going to learn today is a flip-flop. So what is a flip-flop? So a gated latch with a clock input will give us a flip-flop. So flip-flop actually is based on the latch that we were saying, the circuit we were saying for the latch with additional clock input. The sequential circuit output changes when its clock input detects an edge. It can be a rising or a falling edge. So edge sensitive instead of level sensitive. Positive edge is when the clock signal is rising from 0 to 1. A negative edge is when the clock signal is changing from 1 to 0. So the symbol of the clock is a triangle. So triangle, so this is indicates the rising edge of the clock from logic 0 to logic 1, and the falling edge or negative edge of the clock is transition from the logic 1 to logic 0. So this is a triangle symbol that we are talking about. So this triangle indicates this is a clock signal. So without this clock input, this symbol would indicate D-latch, transparent latch. Output follows input. With a triangle, with a clock input, this would be a D flip-flop. Still, output follows input, but on the rising edge of the clock. Because for this triangle, we have this actually indicate is a rising edge of the clock. So when the clock is changing from 0 to 1, on that edge, the output will follow the input. If we want to indicate a negative or falling edge of the clock, we will have a bubble here. So bubble indicate is a negative clock. Okay, so for the positive edge triggered D flip-flop, the function table is listed here. We can see when the clock is on the rising edge, there are two different functions. When D is 0, output Q sub T plus 1. So that is the next moment. So next moment of the output will follow the input. So when D is 0, Q sub T plus 1 is 0. That is a reset function. When D is 1, still on the rising edge of the clock, the Q sub t plus 1 is going to be B1. So simply follows whatever states is the input is. So that is what we call the set function. So the Q over bar sub t plus 1 is the complementary state of Q output. Okay, so there are other three situations here. So for the other three situations, we don't care what the input D is. So that is when the clock signal is 0 or 1 or the following edge. The output, the function are the output functions are inhibited. That means the output will remains the same. So it will be the Q sub t, means the value remains the same. So that is when the previous value is 0, it remains 0. When the previous value is 1, it remains 1. So the output Q sub t plus 1 remains its previous values. So this is the inhibited function here. So that means whenever the clock signal is on this rising edge, the D flip-flop function is a transparent flip-flop function. Whenever the clock is either high or low or falling edge, the D flip-flop output won't change. So this is the transparent D flip-flop function. For the circuit, hopefully this looks familiar. So this, so if we have a look at this part, so this middle part and this output part. So the output part is active low input SR latch. So we learned SR latch last lecture, and we learned two types of SR latch. We have active high SR input latch and active low SR input latch. So this is active low SR input latch. And the middle point here, these two NAND gates give us the enable, an additional enable function to this active low SR latch. So that gives us the combined circuit, gives us a D latch. So in addition to this latch here, we added, so we here have the added edge detector. So this edge detector is used to detect the rising edge of the clock signal. And we are going to talk about the details of this edge detector circuit later. So for now, you know, for the D latch, by adding the edge detector of the clock, we have the D flip-flop. Okay, so for the edge detector circuit is a circuit that converts an active edge of clock input into a brief active level pulse. So it's a very narrow pulse signal that enables, that detects the rising edge or the falling edge of the clock signals and enables the D latch. So it can be created using the gate propagation delays. Let's have a look, the circuit. So we have the input X, that's going to be the clock input signal. And the input will be passed through the NOT gate and then AND with the previous X. So follow the, after the NOT gate, it will be X naught. And this X naught signal will be ANDed with the previous X signal. So this output Y will be our edge detect signal. So for the timing diagram, we have a look at the X input here. So when this X when this X changes from logic 0 to logic 1, it will pass this first NOT gate. Remember that any gate, any logic gate will have a very small propagation delay. So this X naught will change value after a small propagation delay. That is indicated by this green region. So this X naught won't go from logic 1 to logic 0 without a small data delay. So this green region indicates that delays. And the output Y is X and X naught. So at the beginning, when X rises from 0 to 1, X naught hasn't changed from 1 to 0. So Y will be 1 for a very brief time period. So that narrow window of Y equals 1 gives us the short enable pulse signals. So this is the edge detector circuit. So we actually utilize the propagation delay of the NOT gate here to generate this short window of enable signals for the edge detector. Okay, so remember this is a propagation delay of the NOT gate. It's not the propagation delay of the AND gate here. So we are utilizing the propagation delay of the NOT gate in this circuit to create this short window of the pulse signal to generate the short enable pulse signal of the output Y. Okay, so latch and flip-flop behavior. Let's have a look at how these two are different. The latch transfers data from the data input to Q on either a high or low voltage level at the enable input, and that is level sensitive. The flip-flop transfers data from the data input to Q output on either the positive or negative edge of the clock. So that is edge sensitive. So the symbols of latch and D flip-flop are listed here. So for the latch signal, we have the enable signal, which is the level sensitive signal. So for the D flip-flop, we have the clock signal, which creates the edge sensitive output. So we have the output of the latch. In this schematic, we have the same input D, and the clock signal is used as the enable signal for the latch, but it will be used for the clock input for the D flip-flop. For the output of the latch is Q underscore latch, and the output of the D flip-flop is Q underscore flip-flop. Okay, let's have a look at this timing diagram to compare the differences between D latch and D flip-flop. So for the D input, they are the same D input. And for the clock signal, we have the same clock signal as well. So for the Q latch, so Q latch is enabled when the clock is a logic high. So Q latch will follow the input state of D whenever the clock signal is high. And when the clock signal is low, it will remain its previous value. Let's see if it does the correct output for us. So the Q latch at the beginning is 0. The initial value is 0. D input is 0. So at this time point, D input changes from 0 to 1. But the output doesn't change because it's not enabled. The latch is not enabled. So it will wait until the clock signal changes from 0 to 1. So the output latch, Q latch output will change to 1, follows the input D when the clock signals changes to 1. So that is enabled. So when the clock signals change back to 0, D latch output won't change because it will remain 1 until the next rising edge of the clock. So before the before the clock changes to high, so the D input change from 1 to 0, but the output of the latch won't change because at that point, the latch is not enabled by the clock input. So until the clock input changes from 0 to 1, so that means the latch is enabled again. So the output of the latch follows the input D. It will falls from 1 to 0. So this is the latch. So that is the latch output. Let's have a look at the D flip-flop output. For the D flip-flop, instead of the level sensitive, we only need to look at the D flip-flop input on the rising edge of the clock. So for the D flip-flop output, so when the clock input rising edge, we have to look at what the input value is. So on this first rising edge of the clock, the D input is high. So D flip-flop output will follow that input value and then change from 0 to 1. And then we will just ignore anything in between, jump to the next rising edge of the clock. So at this edge, we will go see the input of the flip-flop. And then at this point, the input D is 0. So the output of the flip-flop will change from 1 to 0. Okay, so this is basically the definition of D latch and D flip-flop. It just happens that for the first example, both D latch and D flip-flop output are the same. So the output of these two can be the same under certain circumstances. The following example, we will see they are going to be different. So this is how we find the differences between the D latch output and D flip-flop output. So let's have a look at the second example. So for this example, you can see that D input changes in the middle of the clock high. So the D input value changed from 0 to 1, like not before the rising edge of the clock, but after the rising edge of the clock. So when it does that, D latch will follow the input. So it will follow the input immediately after the input changes from 0 to 1. Because when the clock input is 1, this D latch is enabled. It is level sensitive. Have a look at the output of the D flip-flop. It doesn't change. That is because the D input remains 0 on this rising edge of the clock. So the D flip-flop output can only change values on the rising edge of the clock. So because the input missed the first rising edge of the clock, the D flip-flop output can only change on the next rising edge of the clock. So on the next rising edge of the clock, which is here, the D flip-flop output will follow the D input values. So this is a very important behavior difference between latch and flip-flop. Depends on the application. Sometimes we will need a latch, sometimes we will need a flip-flop. So in our design, you may read from some recent textbook that especially Xilinx technical documents for the last 15 years, or I would say for the last 10 years, for the last decade, you may read the Xilinx technical documents. It will tell you, or they will tell you that try to avoid latch. Try to make sure that all your design is going to be based on flip-flop. That is because the trend in the previous 10 years is to make sure that we have to synchronize everything in the digital design. Why is that? Because we want to improve the operating frequency, improve the speed of the design. Recently, if you read artificial intelligence or machine learning news, you will find that artificial neural network that we implement right now, especially the spiking neural network that is very popular right now, will need the asynchronous application. So if it's asynchronous, then latch will be more useful than the previous flip-flop. So that is additional knowledge here for us. So it's related to the state of the art technology. So in the past, when I teach 384 and FPGA design, I used to tell my students, tell you that we will be focused mainly on flip-flop design, because we will only design synchronous circuit to improve the efficiency of the circuit. In other words, the speed of the circuit. But in the future, I would say we probably will be implementing latch more and more for the spiking neural network, or for the other artificial neural network applications. So I won't, so technology advances, and we have to adopt our design to the latest technology. Okay, so that is the differences between latch and flip-flop. Let's have a look at a few examples of flip-flop. The most popular flip-flop is actually the simplest flip-flop. That is the D flip-flop, and that is what you will find in the FPGA hardware. So in the Zinc 7000 series FPGA, which is on the board that you're going to use in the lab. GK flip-flop is another type of flip-flop. We have to look at the GK flip-flop and the T flip-flop to see the variety of it. So GK flip-flop, it has two input with no illegal input state. So with J and K both high, the flip-flop toggles between opposite logic states with each applied clock pulse. So we have two symbols here with the triangle indicate this is the clock input. This indicate is a positive edge triggered GK flip-flop. And with the bubble on the inputs of the clock, it indicate it's a negative edge triggered GK flip-flop. Okay, so this is the function table of the GK flip-flop. Let's go through this line by line. First, let's have a look at the clock. So for this negative edge triggered GK flip-flop, it only functions on the falling edge of the clock, So this is the downward arrows indicate it's a falling edge of the clock. When G and K are both 0, there is no change for the output. So Q sub T equals Q sub T plus 1 equals Q sub T means the values remains the same on the output. When G equals 0, K equals 1, the output is 0. That is a reset function. When G is 1, K is 0, the output is 1. That is a set function. When G and K are both 1, the output toggle, that is the toggle function. So the output is the QT naught. So it will be the complementary values of the previous value. So that is the GK flip-flop function. So when the clock is either low or high or on the rising edge of the clock, doesn't matter what J and K input values are, the output will remain the same values as before. So that is the inhibited function. So basically the GK flip-flop is disabled. You can see that, or inhibited, it's the same thing. So this is the function of GK flip-flop. Okay, so you don't need to remember this function table. If I want you to do the question based on GK flip-flop, I will give you the function table for any design based on GK flip-flop. If you are going to have the questions in the quiz or exam. Okay, negative edge triggered GK flip function table. Based on that, we have this timing diagram. Let's have a look at the different functions. For this one, we have the negative edge triggered, so that means the falling edge of the clock. Remember, we only need to look at the input on the falling edge of the clock. I can put it this way. So for the flip-flop, you only need to go look at the input value on the falling edge or rising edge of the clock. It's like any other time when the clock is high or low, you don't even need to look at the input values. You will always make sure that the output follows whatever the values, whatever its previous value is. So let's have a look. So for this one, before this first falling edge of the clock, so in this region, the output will remain the same. The output will remain the same. On this first falling edge, you will look at the input value. So the G value is 1, K value is 0. So that is set. That is set. So set means we are setting the output to 1. So output will change from 0 to 1. So the Q naught simply is the complementary value of this Q. And then after that, the output will remain the same until the next falling edge, which is the second falling edge here. So as the second falling edge, we have a look at G's value is 0, K's value is 0. So based on the function table, G equals K equals 0, that is no change. So the Q's value remains high, no change, until the next falling edge, which is the third falling edge here. So at the third falling edge, G's value is 0, K's value is 1. So that is a reset. Reset means Q's value is reset to 0. So that is this transition here. So it will still remain zeros until the next falling edge, which is the fourth falling edge here. So at this falling edge, we still have G is 0, K is 1. So it's another reset, but we know that it's already 0. So reset is still going to give us 0. And that is Q equals 0 until the next falling edge, which is the fifth falling edge. So at this falling edge, we have G is 0, K is 0. That is no change. So at this point, we have no change. That is why Q remains 0. Although Q is always 0 here, but the function is actually different based on JK's value, So if I ask you to draw this timing diagram, you need to draw this output of Q, but I would like you to also indicate the different function here on each falling edge. So we had a look at this different function. Let's move on to the toggle function here. So at the ninth falling edge, which is over here. So the ninth falling edge, we have G equals 1, K equals 1. So that is a toggle function. So previous value of Q is 1. So at the falling edge, the ninth falling edge, it needs to toggle. So that means change from 1 to 0. So that is the toggle function here. And because we keep J and K equals to 1 for the next three falling edge of the clock. So at every subsequential falling edge, the output Q will toggle. So that is the output toggling function. So this is the example of the GK flip-flop. Based on the input of J and K and the falling edge of the clock, we can generate different functions. Okay, so I'm going to let you do this in your own time, okay? So for the same example, this is the falling edge of the clock. If we are going to use the rising edge of the clock, so that means the positive edge triggered GK flip-flop. For the same input example here, you will be able to generate the output, a different output timing diagram for a rising edge or positive edge triggered GK flip-flop. And for that one, you will need to write down the function for each transition for the output. So I will let you to do that in your own time for this example, just maybe after the class, okay? So for the toggle application, we can use it to divide an input frequency in half. So that's the basic function for creating a counter. We will learn the counter design in the next chapter. So, but all counter designs are actually based on the toggling function of each bit. This is also related to the pattern. So following special pattern to count the number of combinations of n-bit input for the digital logic. So we are actually having the toggle application for the GK flip-flop. So this is one simple example of how to use a toggling function to create a counter. So what we have here is the three GK flip-flop. All of them are using the negative edge triggered clock. So the input of these three GK flip-flop are all set to 1. That will give us the toggle function for all the 3 GK flip-flop. So every clock falling edge for the first GK flip-flop, Q0 will toggle. So every time Q0 change from 1 to 0, that is the falling edge of Q0, that will trigger the second GK flip-flop to toggle its output. And similarly, for Q1, when this Q1 change from 1 to 0, that will give us a falling edge for this input of the third GK flip-flop. That will create the toggling of the Q2. So it's a chained GK flip-flop that will give us the counter. So the timing diagram of that previous circuit looks like this. We have the falling edge of the clock that will trigger the toggling of Q0. And the falling edge of Q0 will trigger the toggling of Q1 from 0 to 1. Again, the falling edge of Q1 will trigger the toggling of the Q2. So how does this give us a counter? The counter is a 3-bit counter. So we have Q2, Q1, Q0. Basically, Q2 is the most significant bit. Q0 is the least bit. So at the beginning, we have 0, 0, 0, then followed by 0, 0, 1, and followed by 0, 1, 0, then by 0, 1, 1. And we can count all the way from 0 up to 7, actually. So this is 0, 0, 0, up to 1, 1, 1. And then it will cycle back to 0, 0, 0. So this is a 3-bit counter. Okay, so this is the first counter we design with the JK flip-flop. Okay, so synchronous versus asynchronous circuit. As I mentioned before, these are related to our latch and flip-flop. So we'll have a synchronous circuit, have a sequential element whose output change at the same time. What does it mean by the output change at the same time? Is when we connect all the clock signals together to synchronize all the flip-flop to make sure that all the output of the flip-flop change at the same rising edge or falling edge of the clock. So that means we are synchronizing all the output together. So that is a synchronous circuit. Asynchronous circuits have sequential elements whose output change at different time. So what does that mean? That means when we are using latch, so the output won't be changing at the same time. Depends on when the input changes value, the output will follow the input. Whenever the latch is enabled. So that is the asynchronous circuit. In this case, in this example, the schematic shows us the synchronous circuit because we are connecting all these 3 JK flip-flops clocks together, and we are using the same clock input. And in this case, we are using the rising edge of the clock input. So the 3 output, Q2, Q1, Q0, are actually changing at the same rising edge of the clock. So this is a synchronous circuit. And the timing diagram also indicate that all the rising edge, at the rising edge of the clock, all the outputs change values together. So that is the synchronous circuit. The disadvantages of the asynchronous circuit is difficult to analyze the operations because if you have a complex combinational logic, there are many different gates. So gates will have its own propagation delay. So you have to make sure that the delay need to be long enough. So you have to wait a certain time before all the propagation delays are met to make sure that you have a stable output. Otherwise, the output will have a lot of up and down, passing the different levels of gates, then settles at the longest propagation delay. So the intermediate, that is the intermediate state. So the intermediate states are caused by the different propagation delay of different logic gates. So for asynchronous circuit, we normally have to wait for a certain time of period before go checking the output state. On the other hand, if it's a synchronous circuit, we know that every output will change at the same rising edge or falling edge of the clock. So there will not be the disadvantages of the asynchronous circuit. Okay, so synchronous versus asynchronous input. So synchronous input of a flip-flop only affect the output on the active clock edge. Asynchronous input of the flip-flop change the output immediately. So in this case, we will have a look at the example when we have both asynchronous and synchronous inputs. So synchronous input can be overridden by the asynchronous input. So in hardware, we can have two types of asynchronous input. That's the preset and clear. So common cases, we have active low asynchronous preset and asynchronous clear. So that's the PRE over bar and the CLR over bar. So they are connected to two AND gate with active low input, to OR gate with active low input here. So, so this is the flip-flop asynchronous input. What do we mean by asynchronous inputs can override synchronous input? So we can see from these examples, this function table of the GK flip-flop. So when the PRE and CLR over bar, they are both low, both high. That means they are inactive. The flip-flop will operate synchronously as what we saw before. So we won't go through that. We will have a look at the other three functions here. So when PRE over bar is 0, that means it's a preset. So it doesn't matter. So CLK, J, and K, these other synchronous input don't care. So we don't care the other three synchronous input. Whenever this asynchronous PRE over bar input is 0, output is set to 1. So this is a preset. This means this asynchronous input override the other synchronous input. Similarly, when PRE over bar is 1, CLR over bar is 0. Again, we don't care the other synchronous input. The output will be cleared. So the output is set to 0. That is cleared to 0. So the other functions, when both of them are 0, is a forbidden state. The output will be set to 1. Forbidden means you can't both set and reset the output. So it's simply the forbidden state. Okay, so this is a simple fact you need to remember. That is asynchronous input will override the synchronous input, and asynchronous input, I'm going to ask you now, have a think about it. We see that synchronous input based on clock, they are edge sensitive. That edge is the rising edge of the or the falling edge of the clock. So for the asynchronous input here, we have PRE over bar and CLR over bar. Are these two level sensitive or edge sensitive. So are these two level sensitive or edge sensitive? Time-wise, I won't give you too much time to think about it. And I can tell you now they are level sensitive. And that is why they can override the synchronous input. Because synchronous input, they are edge sensitive. So asynchronous input, they are so they will be edge sensitive. So this the output based on the asynchronous input will be the level sensitive. That's why it will override the adding of the asynchronous output result. Okay, so for this GK flip-flop asynchronous input timing diagram, I won't go through all of it. We will just have a look at one example here. So have a look at the first PRE over bar. When this is high, is so inactive. So whatever occurs here follows the previous GK flip-flop rules. When the PRE signal is 0 now, so that is an active preset. So the output Q will be set to 1. But you will see that this PRE will override the previous output of the Q output that was set by the falling edge of the clock signal. So this is how it override the synchronous clock signals by preset the Q output to 1 here. Because you can see that at this moment, we are not having the falling edge of the clock. So I will let you go check, go follow this example to see the clear signals effect on the output of the GK flip-flop. Master reset is in the circuit, in any design, you will find the master reset. It's a design, is an essential design signal. Normally, we just connect all the clear signals to the D flip-flop together. That will generate a master reset to the circuit. So whenever that signal is set to 0, it will clear all the values of the D flip-flop. So that is a master reset. The circuit is also simple here. The clears negative CLRN, that is the CLR over bar. They are connected all together to this reset signal. And the reset signal here is the master reset in the circuit. Whenever a master reset is active, it will reset everything back to the default value. Okay, so T flip-flop is a very simple flip-flop. It's a toggle flip-flop. The output will toggle on each applied clock pulse when a synchronous input is active. So it has only one input T and one output Q. So the function table is also very simple. In this case, we have the rising edge of the clock. When T is 0, the output won't have any change. When T is 1, the output toggle. So this is the basic function of a T flip-flop. So that is on the rising edge of the clock. On the other cases, so in the other cases, when clock is low or high or falling edge, output is the function is inhibited and the output will follow the previous value. So it won't change. So this, you can see the values remains the same. These are, although the functions are inhibited. So timing diagram for the T flip-flop function is also very simple. So so we can see that when the T value is 0, output will remain the same, 0, when the clock toggle. When T is 1, output will toggle on each rising edge of the clock. So when the T value changed back to 0, the output will remain the same. So this is the simple T flip-flop. In PLD, which is the programmable logic device, flip-flop are usually found. So you normally just find one basic flip-flop. That is actually the D flip-flop. And we also call it the transparent flip-flop. Output following the input on the rising edge or the falling edge of the clock signal. Okay, so I think I'm running out of time. We have a few more slides here. Most of those slides are actually not quite relevant anymore because it's very specific to certain device and certain circuit. What we can do is we will have some practice in the lab to see how the Xilinx 2 will create the circuit using D flip-flop. Okay, so I will stay here and answer your questions. Okay, primitive. Primitive is if you use the library template, the primitive is something's already defined as a component in the library, and you call that library function. Basically, if you see, you know that we have some functions already defined there, so we call it a primitive. In HDL, a primitive is similar, but it's not just a function, it's a component. So that means it's, for example, the latch primitive. When you call that latch function from the library, the components has already been wrapped together. So if you want to implement that in the FPGA hardware, the synthesis and implementation tool knows that that primitive component needs to be mapped on the FPGA as a certain element, as a certain device like latch or a 4-to-1 multiplexer or decoder or encoder. So it's already previously defined. So that is a primitive. So it's just a predefined function that you call and use it, then it will be mapped automatically on the hardware. So hopefully it's like an IP core. So you will find some books will tell you this is an IP core, or you read the Xilinx technical document, they say this is an IP core. So that also means it's a primitive. Yeah. Okay, that's a very good question. I think I need to maybe mention this again, so to everybody. So Thank you for asking that. Okay, so